In the previous video, we introduced the idea of the substitution property, but we specifically applied it to indefinite integrals. And here I'm going to note that using the same exact idea, we can apply it to definite integrals. The only difference that we would make is when we apply it to a definite integral, we need to go from all x's to all u's. So if we're using the substitution u equals g of x, our lower limit of integration x equals a is going to become u equals g of a. Our upper limit of integration, the b, x equals b, is going to become u equals g of b. So let's see how we would use this in an example. So looking at the definite integral given, we see kind of this function derivative pair, the g of x, g prime of x, which is a good indication to think about a substitution. So you have the 1 plus x squared as an inside function, 2x its derivative outside of it. So I am going to let u be equal to 1 plus x squared. So then its differential du is the derivative of 1 plus x squared, 2x, times dx. So the 1 plus x squared becomes u, the 2x dx becomes du. But we also have to switch our limits of integration. And let's just do that to the side here. So our lower limit of integration is 0. And we just look at our substitution and we think, if x is 0, u is 1. Our upper limit of integration is 1. So looking at our substitution, we know if x is equal to 1, u is equal to 2. So putting everything in terms of this variable u, we will have the definite integral with a lower limit of integration 1, an upper limit of integration 2, and it becomes u to the 10th du. And the really nice thing to note here is that when we're evaluating a definite integral, you're getting back a number that represents a net difference of enclosed areas. And when you do this substitution and you switch around your limits of integration, what we get here is an equivalent definite integral. So with definite integrals, you do not need to resubstitute. So no, there is no resubstitution. Whatever you get when you evaluate this new resulting integral is the value of the definite integral. So by the fundamental theorem of calculus, an antiderivative of u to the 10 is 1 over 11 u to the 11, and we evaluate this from 2 to 1. So we have a 1 over 11 out front, we plug in 2, we put a minus sign, we plug in 1. 1 raised to the 11th power is still 1. And this number that we get back here, that is the value of the definite integral. So let's look at a second example. Now, looking at this integrand here and thinking about how we could integrate it, it looks really difficult, and none of our previous methods, before the substitution property, look like they would apply. And the thing to note is you have this inside function, x squared plus 2x plus 6. And if you were going to do a u substitution, that would be the thing to let u be equal to. So let's try that. If u is equal to x squared plus 2x plus 6, du will be its derivative. So 2x plus 2 all multiplied by dx. And the observation we have to make is we don't quite have that in our integrand. So du needs to be 2x plus 2 times dx. But what we do have in our integrand is this x plus 1 multiplied by dx. So if I go ahead and just simplify a bit, this would be du times 2 x plus 1 dx. So that 1/2 du is x plus 1 dx. So now we can take our integral and put the integrand solely in terms of u. So the x plus 1 dx is going to be 1/2 du, And that x squared plus 2x plus 6 in the bottom is u. So we have 1/2 over u squared du. But note, this is a definite integral, and when we evaluate a definite integral with a u substitution, we are going to have to switch our limits of integration. So let's go about this. Our lower limit of integration is 0. So when x is 0, looking back at our substitution, if each of these x's is a 0, u is simply the 6. So the substitution is what we use to switch the limits. The upper limit, if x is 1, u is going to be 1 plus 2 plus 6. So the new upper limit of integration will be 9. So we get the equivalent definite integral from 6 to 9 of 1/2 over u squared. So 1/2 is a constant that we can pull out. 1 over u squared is u to the minus 2. So this is now a much more reasonable integral. We note that minus 2 plus 1 is minus 1. So an antiderivative of u to the minus 2 is minus 1 over u. So you have a minus, the 1/2 out front, 1 over u. And we need to evaluate this from 6 to 9. So we plug in a 9, we put a minus sign, we plug in a 6. And this number ends up being 1 over 36.